Deep learning is a subset of machine learning that focuses on training artificial neural networks to learn and make predictions from large amounts of data. It involves building and training neural network models with multiple layers, hence the term deep, to automatically discover intricate patterns, features, and relationships within the data. Deep learning has achieved remarkable success in various domains, including computer vision, natural language processing, speech recognition, and reinforcement learning. Here's an overview of deep learning and how to implement neural networks. Understanding neural networks. Neural networks are computational models inspired by the structure and function of biological neurons in the human brain. They consist of interconnected nodes, neurons, organized into layers, including input, hidden, and output layers. Each neuron receives input signals, processes them using an activation function, and passes the output to neurons in the next layer through weighted connections. Deep learning architecture. Deep learning architectures comprise neural networks with multiple layers, allowing them to learn hierarchical representations of data. Common types of deep learning architectures include feed-forward neural networks, FNNs, simplest form of neural networks where information flows in one direction, from input to output layers. Convolutional neural networks, CNNs, designed for processing structured grid-like data such as images, with specialized layers for feature extraction and spatial hierarchies. Recurrent neural networks, RNNs, suitable for sequential data processing tasks like time series analysis and natural language processing, with recurrent connections allowing information persistence over time. Long short-term memory, LSTM, networks, a type of RNN with memory cells that can retain and utilize information over long sequences, addressing the vanishing gradient problem. Generative adversarial networks, GANs, consist of two neural networks, a generator and a discriminator, trained adversarially to generate realistic data samples. Data preprocessing. Prepare and preprocess the data for training the neural network model, including tasks such as data cleaning, normalization, feature scaling, and encoding categorical variables. Split the data into training, validation, and test sets to evaluate the model's performance and prevent overfitting. Model training. Train the neural network model using an optimization algorithm such as stochastic gradient descent, SGD, or its variants, including ADAM, RMS-Prop, or ADA-Grad. Define a loss function to quantify the difference between the predicted outputs and the ground truth labels, and minimize this loss during training. Use techniques such as backpropagation to compute gradients and update the model parameters, weights and biases, iteratively based on the training data. Hyperparameter tuning. Fine-tune the hyperparameters of the neural network model, including the number of layers, the number of neurons per layer, activation functions, learning rate, batch size, and regularization techniques. Experiment with different hyperparameter configurations to optimize the model's performance and generalization ability on unseen data. Model evaluation and validation. Evaluate the trained neural network model on the validation set to assess its performance metrics such as accuracy, precision, recall, F1 score, or mean squared error, depending on the task. Perform model validation and cross-validation to ensure robustness and generalization across different data subsets. Deployment and inference. Deploy the trained neural network model for making predictions on new, unseen data in real-world applications. Integrate the model into production systems or applications using deployment frameworks such as TensorFlow Serving, TensorFlow Lite, ONNX Runtime, or PyTorch Serving. Monitor the model's performance, accuracy, and reliability in production environments and fine-tune as needed based on feedback and new data. Implementing neural networks involves a combination of programming skills, mathematical understanding, domain knowledge, and practical experience in deep learning frameworks such as TensorFlow, Keras, PyTorch, or scikit-learn. As you gain familiarity with these concepts and tools, you'll be able to design, train, and deploy neural network models for a wide range of machine learning tasks.